Welcome. My name is Claire Callender, and I'm Professor of Higher Education Policy here at the Institute of Education. And I'm also Deputy Director of the Centre for Global Higher Education, funded by the SRC. And the Centre is hosting tonight's event along with the OECD's Centre for Education, Research and Innovation. And CG, as we like to call it, is currently undertaking 16 different sorts of projects, all around different aspects of higher education, involving some over 45 researchers drawn from 6 UK-based universities and 8 universities based outside the UK. So CG is a truly global and international partnership. And one of the things that we do look at are issues around teaching and learning, which is really the focus of today's event. Now, the format for today is that Carl Wieman will present his lecture, and that will be followed by responses from 2 individuals. Firstly, and I'd like to welcome Osama Raham, who is the Department for Education's Director of Analysis and the Chief Scientific Advisor. Originally, he was an academic, but has played many roles since then. And most recently, he was Director of Analytical Services and Chief Scientific Advisor at the DFE, and prior to that, the Chief Economist. Also, from home territory, I'd like to welcome Professor John Mitchell, who's Vice Dean of Education in the Faculty of Engineering Sciences at UCL. And he also is the lead on the development of teaching and learning spaces in the new UCL East campus based at Stratford. Professor Mitchell's research is based around access technologies, both wired and wireless. And in addition, he has a keen interest in improving engineering education with a particular focus on introducing student-centered techniques. So Professor Mitchell's interests neatly leads in to the key speaker today. And it's with enormous pleasure that I'd like to introduce Professor Carl Wieman. Professor Wieman holds a joint appointment as Professor of Physics and the Graduate School of Education at Stanford University. He won the Nobel Prize in 2001 and has done extensive experimental research in atomic and optical physics. His current research and work is focusing on undergraduate physics and science education, and he's pioneered the use of experimental techniques to evaluate the effectiveness of various teaching strategies for physics and other sciences. And he's recently authored a book called Improving How Universities Teach Science, which of course is the topic of today's lecture. Professor Wieman, the floor is yours. Thank you.
Oh, thank you. It's a pleasure to be here. I have to say I'm not used to having an introduction that makes it so clear that if it gets really boring, you should pull the fire alarm and be released. But hopefully that won't be that bad. I want to start out by making it clear that my goal isn't to produce a whole bunch more scientists and engineers. That's on it. Some more is okay, but I'm really focused on the broader, let's call it technical literacy for science education that is useful for, I would argue, for really every university student, really regardless of their future occupations, both to make them more wiser citizens in terms of some of the important decisions have to be made in a democracy, and then in the modern economy, so much of the workforce calls upon more technical knowledge and skills. Now, I'll also emphasize my focus, as said, is really on university level education. So if you want to know how to, improve your 7-year-old's education, you're in the wrong talk. But so what I'm going to talk about is first covering basic educational goals and sort of the research-based principles of learning that have come out of research, and then look at applying these principles in a variety of university courses, looking at the kinds of data we get, and then and measuring results, and actually talking, for those of you who are teachers, a little bit about some of these things, some ideas that come out of this you maybe not familiar with, you can use tomorrow. Before I go into those, though, I want to give you a little my own background of how I got involved in this work and sort of my own perspective that I bring to it. And it really came about, my interest in education, not from teaching, or not in the formal course sense, but from working with my PhD students, working in my research, physics research lab. And I got puzzled about this phenomenon. I saw it getting repeated over and over, that these new students, graduate students, would come into my lab. They'd had, many years of great success and outstanding exam scores and so on in physics and mathematics, but when put into doing research, they were really pretty clueless about how to actually do physics. And yet, it wasn't some mental deficiency of them, because they almost all, after a couple of years working in the research lab, turned into expert physicists. And so after I saw this happen enough times, I decided, this wasn't a strange idiosyncrasy of particular students. There was some fundamental issue about learning that was going on here. And this was actually about 30 years ago. And so I decided to tackle this like a science problem. And so I went and started digging into the research on how people learn, particularly how they learn physics. At that point, there was some early research on that subject. And I found out that first, it explained the puzzle. This actually made sense. It also made me realize that there were much better, more effective ways in principle to teach than what we were using in our courses. And then it also got me started on actually doing education research, of realizing you could do experiments, you could collect data and have fundamental principles to explain them. And that was, so for many years, I actually had 2 parallel research groups, and I now have about equal numbers of publications in atomic physics and science education. But my work has always focused from this extent of what's expertise? What does thinking like a physicist or a scientist mean, and how it's learned? And so, when I think back to the goal of education and what I felt my students, these graduate students, were lacking, it was being able to make decisions when faced in this about how to do physics. And so I'm going to now step, way back and ask to frame the question of what's the goal of education? And what I would argue is it's fundamentally about having people learn to make better decisions in some relevant aspects of their life. And at the level of university science education, at the program and course level, it's really about having them learn to use the reasoning and knowledge of the discipline where relevant to make better decisions. Decisions that are like experts in the subject. That's what I call it. That's sort of how you define expertise. And so the rest of my talk is really about research on how to do that, how to teach that more effectively. Now, this is part of something called discipline-based education research, which some of you may have heard of, but it's really a fairly new and not widely recognized subject. And it's really comes from science and engineering faculty in university departments studying specifically the teaching and learning of those science and engineering disciplines. And it's focused purely at the university level, and it's primarily, just for historical accent, been primarily done in North America, although now it's spreading throughout the world. And just a note in passing, since I am speaking in a faculty of education, the research that comes out of this kind of research is actually much simpler and cleaner in its results than the school or K-12 education research. And it's just because at the university level, particularly in these disciplines, it's just a much simpler, experimental system. There are many less confounding variables, and so it's easier to get cleaner results, just like any other area of science. But I would say it's almost certain the principles I'm going to talk about here, though, almost certainly apply at the school level as well, although they may not be as complete as they are at the university level. There could be, just as there are other confounding factors in the research, there could be other factors important in the teaching and learning of it. Okay, so I'm going to start with what the biggest picture of this whole body of research that I'll talk about more, but it really introduces a new paradigm on learning. You can use the reserved seats there. Nobody else will take them. Anyway, learning at the university level. And I'll start, the old and frankly completely prevailing still model of university learning is that these student brains come into our classrooms and we immerse them in knowledge, the curriculum, and it soaks into different amounts depending on what the brain was like, okay? Now, if this is your model of learning, which, as I say, it really is, then the primary focus and discussion of education at the university level is first, deciding on the contents of this knowledge soup, the curriculum of topics you're going to cover. There's lots and lots of discussions always in every department and university about that. And then the second is admitting the best brains, selecting the brains that the knowledge soaks into best, okay? And then, of course, when things don't work very well, blaming the schools for any failures, okay? Now, with this model, though, of really learning, it also has really the idea of teaching as kind of a folk art that's kind of an individual choices, and everybody is an equivalent expert to a large extent. Okay, so what's the research-based paradigm or view of learning? It's quite different. And this is the correct version. This is what research really tells us is happening, is that these brains come into the classroom not actually very different, and that other than soaking knowledge into them, they really are transformed in the educational process. And by that, I mean there's really major changes going on, some new neurons, but drastic changes in how the neurons are hooked together. And it's really in this rewired brain that the knowledge and the learning and the new capabilities of learning take place. And this rewiring is in response to basically intense thinking results in this. And you can actually even see this now with modern brain imaging. These are two people's brains. They're in an MRI machine, and they're interpreting a medical X-ray. And on the right here is a medical student who's just learning to do this. And on the left is an experienced, highly expert radiologist. And I think you can, it's not real clear maybe from where you are, but you can still see that their brains are being activated in very different ways in response to this task. The experts has been changed, and we have some studies where actually a single brain can be measured at different stages of learning, showing that it's actually changing how it's functioning there. Now, there's other things that come out of this, which is that the idea that there's really teaching as expertise. There's really particular ways of teaching that create the right kind of mental exercise that lead to these changes in the brain, and that the teaching methods really dominate the results relative to the content, because it's the methods that really determine how intensely engaged the brain is. Okay, so if you don't take away anything but that, you have a pretty good view of everything more I'm going to say at the high level. So now the rest is sort of details. Now, this view of learning has really come about because of the new insights, more or less in the past couple of decades, from three different fields: the brain research, more the cognitive psychology, this the learning science about how the brain thinks and learns, and then these kind of university classroom studies that I talked about being carried out by science faculty. Okay, so now I'm going to jump into the basic applying these principles and looking at the kind of research studies people have done, the kind of data, or my choice of particularly nice data, illustrating what goes into those conclusions. And so I first want to say that, okay, so there's, I've been saying there's lots of this kind of classroom, science and engineering classroom research. And once you strip away the jargon, of which there's lots, of course, that it really almost, the research, particularly the compelling, comes down to some basic features. It's first, the research develops some test that really probes how well, how experts are thinking about the subject. They make decisions, for the relevant topic and relevant level. And then they take that test and they use it for comparing how well students are learning to do this for two different conditions. Usually, in most cases, the control condition is the standard and still widely, prevailing lecture approach of instructors standing up, telling the students things that they should know, what they should do. Oops. And then the experimental condition is various ways they're having the students practice actually making decisions and getting feedback on those decisions. Now, I think when you boil it down to that level, most people ought to not be too shocked that there's a big difference there between practicing making decisions versus somebody talking at you in how well you are. But I'll just show you the data to convince you a little more. So this is a study I had a little bit of involvement in, which is looking at just learning that takes place in the classroom setting, okay? And this is in a large lecture theater class. It was a very large enrollment physics course, and so you could have two sections carefully measured as being very identical. And then the control, one of those sections, was then taught this particular material using by a very experienced faculty member who used traditional lectures with had high student evaluations of it. And then the experimental section was then somebody who's a physics PhD, but had then been trained in these methods and techniques of research-based teaching. In my program, actually. And so these two instructors agreed to cover the same material, or try and cover the same material in just the same amount of class time. And then they had a jointly developed test that they gave to the students right after the second, right after the completion of these units. And they carefully timed this so that students weren't doing homework or studying for exams outside. So it was really, by intention, just measuring the learning that took place from the students coming to class, okay? So here's the results. and the histogram of the test scores here versus the number of students, and you can see the distribution is profoundly different. It's actually even more extreme when you realize on this particular test, the amount of learning is kind of a measure of how far above 3 a student is. And so, this makes it clear that the learning from lecture, in this case, and I could show you other cases I've got data on, is just really tiny. But it also, and I want to stress more, shows how this is a way of teaching that's effective for the entire population. You can see the whole distribution has moved up here. So it's not just better for the stronger students or the weaker students. I like to say it's better for all the students who have a human brain, because this is really the way the human brain learns, and that's pretty much all your students, I think. Okay, now you might argue appropriately, well, that was just what happens in class, but most of the learning takes place outside of class. Students are thinking about the material, studying, exams, etc. And you're right. I mean, that was just a research study. Most of the research in this field looks at the learning that takes place over an entire completion of an entire course. And so this is an example of that. This is looking at first-year physics, and what they're doing in this study is they're looking at how well students can use the concepts of force and motion, which are sort of the key concepts of this course, to make predictions like a physicist would as to what would happen in simple real-world situations like cars running into trucks, etc. And so we researchers in physics have developed some good tests that are used widely for probing this. And so they collected data on this for a number of years across these many different instructors and many different sections. And they were scattered here around 0.3, which is pretty typical for a well-taught lecture course on this material that you see. Okay, and then they switched to this research-based teaching, and basically all the instructors and all the sections jumped up dramatically and are now closely scattered at about a factor of 2 higher than the previous average was. And so the point that I particularly want to emphasize here, as it's come out of these kinds of studies, is that you have the same instructors and they simply changing their methods, and that dramatically changes the learning and really is determining the learning outcomes. Now, so what's happening in these experimental classes that are getting so much better results? Well, basically, the format and the details, of course, vary on the settings and so on, but the format's pretty general for most of these kind of studies, which is that the students do some kind of a little bit of preparation before coming to class, and then in class they're sitting there working to solve problems, to answer questions, usually collaboratively, while the instructor is going around monitoring what they're doing, and then periodically, every 10 minutes or so, the appropriate spot is then stopping them working to give feedback and answer questions, and then they continue on down through working through the materials, answering questions for their problems. So let me just show you what this looks like in the large lecture setting, where it's a little trickier to figure out how to do this effectively. So, but this is like in the first study I showed. This is an example of what they were doing there. So they have this reading assignment they're supposed to do before class, and just to emphasize that what's really happening here isn't them learning the physics, but it's essentially moving the basic, information and terminology, not wasting class time with things that they can get perfectly well reading on their own ahead of time. And then class starts not with a lecture, but starts with a question. For example, this is one that was used. You have this where teaching about basic electricity here. You have a circuit with light bulbs and a battery, and the students are asked what's going to happen if that switch is closed to the brightness of bulb 2. And then every student, because you want, use technology here, every student has a clicker, which I don't know how familiar people are with. It's basically, it looks something like this with 5 buttons on it, and every student has one. And they push the button, and basically my computer as instructor records who they were and what answer they chose, okay? And then they would discuss, so in this class, these 2 and those 3 would have to talk to each other about what the answer was and the reasons behind it and re-vote. And while they're doing that, the instructor isn't standing up here waiting. They're actually going up and down the aisles, listening in on those conversations to get little snapshots of what's going on in those student brains, what aspects of their thinking is like a physicist, like they want, or what aspects are incorrect. And then, so then after they've re-voted, takes discussion, a couple minutes, then you demonstrate the results and show what happens. But then there's important a follow-up summary in which the instructor then gives feedback to the students on the models they're using and what was right and what was incorrect in their thinking. And I emphasize in particular that this is in bold because a lot of instructors who aren't so well educated in learning, the students will answer, and if some of them will write and a bunch of them are wrong, will then think the appropriate thing is to they'll go over, here's carefully what the correct answer is, and they'll move on. In fact, that doesn't achieve much learning. What really achieves learning is when a person does something incorrect and then has come to understand why it's incorrect and how to change it. And that's really where learning is produced. And so it's really critical to spend actually more time on the incorrect answers and why people are thinking about that than it is the correct ones. Okay, so that's the basic idea of what would happen. More mathematical things also in a large class, or especially in the smaller classes. People are having worksheets where each student is writing things down, calculating, and so on, but they're talking to each other. The same basic process is happening. And so in the small class that I showed you, there were 40 students. There, in those settings, usually people are having the students sit around tables and so on and work together. But the same cognitive operations and feedback operations are happening. Now, okay, so how is this helping students learn? Well, if you think about it, they're practicing thinking like physicists. They're doing, because what they're having to do is look at that question, they're having to choose and apply a conceptual model, test it against what happens, test it through their arguments, discussions with their fellow students. So that's very much, physicist thinking, and they're getting multiple immediate forms of feedback from their fellow students, from comparing their predictions with what happens, and then from the informed instructor who's targeting. And so those are really the key aspects of why these things are much more effective for learning. Just to show you, it's not all physics, and it's not just in measured concept tests. This is applying the same ideas to introductory core computer science courses at San Diego, where the same faculty then switched over to essentially exactly like I described with the electricity example. These are big classes using clickers and questions. And they looked at the drop in failure rates here. And basically, you can see across the board, the adopting these methods led to decreased failure rates. And so, again, you have the same people, they've adopted better teaching methods, and now they have about a third the failure rate they did before. That means a lot of students are now successfully able to pursue careers in computer science who weren't when the faculty were just less effective teachers. Lots of research has been done on introductory courses. and people think, well, advanced courses are different. They're not. This is something my own group has been leaders on, of applying these same ideas in advanced classes. Those are more like the small ones. You know, they're smaller classes. They're much more mathematical, so students are working away, calculating these things in worksheets, while the instructors are, you know, going around monitoring what they're doing, but again, periodically stopping and giving very targeted feedback to the students. Does it work? Yeah. So here's one standard deviation improvement for, this is a 4th-year course, just to show you data. At Stanford, we have, with some nudging from me, now so a large fraction of the courses in the 2nd to 4th year that physics majors take have actually been transformed to this kind of research-based teaching. And it's very striking, basically, how there's been very strong both student and faculty preference for this kind of instruction. Okay, so those are a bunch of examples. The big overview is, if you dig into the full literature across all these different STEM fields, you can come up with about 1,000 experiments doing these kind of comparisons of traditional lecture with these various research-based instruction. And they show that the results are really dominated by the teaching methods that are used, and that they consistently show greater learning, lower failure and dropout rates, and they're somewhat larger benefit for at-risk students, although the data is not quite as strong there. But I want to emphasize now that there's actually a lot of factors that go into getting really good results, and big differences here. And so this is sort of now the background. Now this is kind of the educational part of, here's all the things, if you want to be a really effective teacher, you've got to pay attention to, okay? And these are all things that research shows, if you do these things, you get better results than if you don't. So at the center here is the students have to learn, or they have to practice making decisions, and they have to have feedback that's timely and specific in terms of helping improve their learning. But then in terms of what kind of exercises and decisions they're making, there's a bunch of things that are important in those designs, and those are the things all across the top here. There's the appropriate level connection with the student's prior knowledge. There's making motivation. These are, if you want them to learn, they have to be intensely engaged, because otherwise their brain's not getting exercised enough. So motivation's critical. There's some basic brain constraints I'll say a little more about. And then finally, there's got to be the disciplinary expertise. It's not enough to just tell them to go work on problems and talk to other students. They got to be practicing the important decision-making, important thinking for the discipline relative to the topics being covered. And then there's down at the bottom, there's research on important aspects of implementation, the kinds of questions and deliverables you have to have, and how to enhance the collaborative or social learning between students working together. But within this slide, all the things covered in those boxes, what I argue is that it allows one to do something that really is only quite recently possible, which is that it really allows you to define teaching expertise at the university level. And in the same way we can now define, expertise in medicine and some, various other professions. Now we can say, look, if you're an instructor and you use all of these practices, you know about them, you will be a bit more effective teacher. You'll have better student outcomes than if you don't. Okay. So I'm going to say a little bit about a couple of these just that you might not be so familiar with. I think these people have a pretty intuitive idea of what's involved in that. The brain constraints are one that is useful to know about. There's really two aspects I want to talk about. First is it has to do with working memory. And in terms of the way cognitive psychologists think about the brain remembering things, they talk about long-term memory. That's what most of us think about as basic memory. It's got this enormous capacity and it works for long time scales. But on learning new things and on short time scales, there's this buffer essentially that before the long-term memory, and this is the so-called short-term working memory. In contrast to the long-term memory, it has a tiny capacity, something in the order of 5 to 7 new things, which means new is not in long-term memory. And every additional thing that this buffer working memory has to deal with reduces what it can pay attention to, reduces its processing, and reduces the subsequent learning. And so any additional thing that comes along has a price, is what this means. And so you can look at a bunch of things that happen in the classroom. And first, the split attention, which is just a disaster for learning because it dramatically drops the available working memory, available for the content you want to be learning. And so even if you don't believe anything else about this talk, if you are sitting there giving lectures and a whole bunch of the students are busy checking their phones or the computers, which in the modern world is a real big problem, get somebody to look from the back and check, it's just a total waste of time for everybody concerned. Okay, but there's some other things that aren't so obvious and are more under the instructor's control. Every bit of additional jargon is loading down that working memory. So you need to think really hard whether that term is all that important to use, because it will have a cost. But then the thing that gets teachers and students particularly upset when I point this out is all those interesting little digressions and those jokes, they actually hurt learning. And the students will say, but that can't be, that's the only time I pay attention. And the instructor will say, that can't be, that's the only time the students pay attention to me. But that's exactly the point. Because of this limited capacity for attention, anything the students are paying attention to means they have less attention devoted to actually learning the material, okay? And so just keep in mind, everything has a cost. So it doesn't mean you can't have jokes, but that joke has to really, deeply involve the nature of the content you want to be learning, because if it's different attention, then that hurts. Okay, the second part has to do with long-term memory, and retention. Obviously, we want our students to, we teach them and we expect them to remember that for 30 or 40 years, or at least a few weeks. And so they know a lot about retention. And it turns out that the problem really isn't getting stuff into long-term memory. The problem is recalling it back out when you need it, okay? And where that comes into important in teaching is that as the brain learns new stuff, that interferes with its recall of the previous stuff, okay? Because it's building up new neuron connections that get in the way and so on. And so if you think about this sort of standard process that happens in courses, you cover chapter 1 material and the students do problems on that and maybe have a test and they've mastered chapter 1, great, and then you go on to chapter 2 and chapter 3 and so on. But in fact, by going through chapter 2 and 3, that now reduce their ability to correctly recall the material from chapter 1. But fortunately, once you know about this, it turns out it's pretty easy to fix. That this interference and recall, if the brain just occasionally goes back and has to remember that chapter 1 material as new stuff is coming in, it cleans up all of those interfering connections, and so it suppresses the interference. So for any physicists in the audience, it's a really good analogy to doing a quantum measurement, so you get a clean quantum state. But for those of you not physicists, just take my word for it. Thinking about chapter 1 while learning chapter 3 is really helpful, okay? Okay, so then the other thing I want to talk about is what's the nature of how to think about what the disciplinary expertise should go in here. And I talk about that just because my own group has been doing a bunch of research lately that's very relevant to this and pretty interesting results. We're looking at expert problem solving. And so in that we've been looking across science, engineering, and some medical fields, and we're identifying the decisions that experts make in those fields as they're solving authentic problems, in their discipline. And so the first step of this is identifying the decisions, and then we're working to use those decisions to create better assessments of how well students are learning to think like experts, with the ultimate goal of improving how that's taught as well. So what we've done, and this is quite recent work, is interview a whole bunch of experts across this range of disciplines. We're up to almost 60 now. Interview them in which they go through in detail the process of solving some, significant problem that they've done and, fairly recently, okay? And then we code the decisions, all the decisions that they made in going through that problem-solving process. And skipping details, this turns out you need a team with expertise across a bunch of different areas. Fortunately, I've been able to assemble that. And what we found is really quite surprising, is that across all these fields, they all make the same set of decisions. And for every problem, they make the same set of decisions. And so there are 31 of them that, a mechanical engineer, a physicist, a biologist, a doctor doing diagnostics, they make the same 31 decisions in that problem-solving process. Now, emphasize the decisions are the same. How the decisions are made, what they come to as decisions, those are very different, very discipline specific, use all kinds of knowledge and can be quite individual, but it's been remarkable to emerge that the decisions themselves are the same. And I sort of lumped them into roughly categories here. They delineate the goals of the problem, how to frame the problem, deciding, they decide how it relates to other problems they know about and potential solutions, deciding how to decompose the problem, what simplifications or approximations they can make, priorities, and so on. So, if you're in any of these fields and you solve problems, you'll look at this and say, oh, yeah, I do that. But it's just fascinating to realize they're all doing that, okay? And in terms of deciding what information and then how to correctly interpret and analyze it, decide about the reliability. So what does this have to do with what I was just talking about teaching? Well, it means that if you want the students to learn to think about and solve problems like an expert in the discipline, you need to have them practice making these decisions. And so, for example, if you think about any area of science and engineering, you think about, you should give students the problem, the decisions when, and given the question or problem, deciding, what concepts are relevant to that problem, deciding what information is relevant to solving it and what's irrelevant. I already mentioned deciding how to decompose it, deciding what approximations are appropriate. and deciding on and criteria for potential solution methods, and then you can put in as many others you want for any particular problem, but one that's really critical, shows up as very important for everyone, is at the end deciding, once you get a conclusion, each discipline has criteria, deciding that meets the disciplinary criteria for that conclusion making sense or the answer is reasonable. Okay, so while these are what I would argue is you should have these as a fundamental part of what the problem students are practicing solving, if you actually think about those, the typical science and engineering problem explicitly removes all of these particular things because they're too fuzzy. People want to give nice, clean, simple model systems, where everything is, all of these things are obvious. In doing that, you're basically completely removing the students from this essential practice of problem solving. Now, I will say the other thing in our work, we've now started having these decision-based assessments where once you realize, this is a key decision needed for this subject, it's really easy to map it onto simple scenarios, ask the students what their decision is and why, and it's very, very clear when they are like, or more often completely not unlike, experts in the field. And we see, most of the time these are, highly successful graduating Stanford students, medical students, and they're terrible at using this knowledge to make decisions, which is really what you want from education. Okay, so what am I doing time-wise? Okay, so let me say a little then quickly about some of the research on implementation and some things that have been shown to be important there. First, it's I'm picking out things where I've seen faculty hear about these techniques and go to use them in their courses, but kind of miss important elements. And so this is one of them. They, in the design test, it's really critical to have clear deliverables, something the student actually has to do, basically, to get them deeply engaged and to see what they're doing. And then the second aspect of the implementation is, it turns out almost all of these things involve working in small groups. That's just because it's an easy thing to do and there's such clear gains from doing that. But I think it's important to understand actually what really contributes to those gains so that you're actually implementing it effectively. So the first that most everybody sort of recognizes right away is that, okay, if they've, you got 3-4 students, they can get feedback from their peers or some missing piece of knowledge that the more, better prepared student can tell the less prepared. And so they can get sort of more immediate feedback. They can avoid spending a lot of time being stuck. And so that part's kind of obvious. But there's actually a really more important part that's not obvious and well known by a lot of people, but very well studied by the cognitive psychologists. And that is that when somebody's going to explain something to somebody else, even just preparing to explain it to someone else, it actually triggers a different cognitive process in their brain. And the brain sort of has special wiring, if you like, for this kind of social interaction. And so it's really fascinating that people do these experiments where they'll have these, 2 people study something, and then, or let's take one person, they'll study it, and then they'll either be given a case where they study it some more, or they spend that same time actually preparing it to teach to somebody else, and then they test them on the material. And just the process of preparing to teach it, they learn more. You test them on it, and they score higher, okay? So So there's really a basic learning process just from the fact that you're putting them together to interact. And then finally, also overlooked a lot of times is this is incredibly useful for a teacher to have students bring together just so you can listen in on those conversations. You can get so much better idea where their brains are, and then that makes you a much more effective teacher. You can be much more effective feedback. And so that's kind of the group learning benefits to take in mind. So, start wrapping up here. I think the conclusion is basically that we have this substantial body of research now, which is really established, teaching expertise. What practices are fundamentally more effective, and we understand what they are and why. And when they're learned, by the instructors, instruction staff, and applied, students learn more. And what we've seen in doing these large-scale experiments, I'll talk about it again, both students prefer, it varies on conditions, how much, but the faculty really prefer it once they learn how to do it there. And so, I'd argue this has the potential to really dramatically improve post-secondary education, but it raises the question of how to make this the norm, what we, basically the medieval model of universities we have now to something modern research-based. And so I'll just finish up saying a little bit about this big experiment I did, kind of trying to figure that out. And so this was the Science Education Initiative, which was targeting large-scale institutional change in teaching, and had 2 big public research universities. The details are all in the book I ended up writing here. But, it was successful to the extent it did change some entire departments, or at least 90% of the faculty dramatically changed how they teach. And between these institutions, that was several hundred faculty members in the sciences and most of the credit hours they teach. And we also were able to show that once faculty learned how to do this effectively, they overwhelmingly preferred it and continued to do it even when there was no incentive or support to do so. And as a note that every administrator cares about, we showed it doesn't cost any more, in terms of the instructional costs. They're just the same. But the key element really has to do with the finding that the formal evaluation incentive system really penalizes faculty for doing this. That the time they take away to learn to teach more effectively comes at a small cost to research productivity. That's the only thing the evaluation system basically measures and rewards. And so it's really, to move this thing to a large scale, it's really essential that universities find a way to really better measure teaching expertise and reward it, okay? And so I believe that the fundamental problem at this point is a better way to evaluate teaching. And it has to be a way that captures the use of these best practices in teaching that research shows lead to better outcomes. And so just say, one last point about this is that across the whole world, the teaching evaluation is dominated by student course instructor evaluations. I can go through a lot of research on that, but the bottom line is they do not reflect the amount of learning, and they don't reflect the amount of the use of the most effective teaching practices, and they are subject to lots of biases, in particular in in fields like chemistry and physics that are male-dominated. There's a strong bias, gender bias, against female instructors. So people got to do, it's just, okay, time to do something better. And I've written various articles. You can learn about this, but I'll just finish here with talking about, here's the, if you want to learn more about this, here's sort of my list of favorite references, some books on the basic underlying ideas, and then at this website, we have a lot of resources for faculty where it's sort of 1- and 2-page guides. If you want to implement some specific thing, this gives you the details of how to do it. So now there's going to be time for questions, but I'm going to start by asking the first question.
We're going to do that afterwards? We're going to have a
No, I'm going to ask this question first, okay? Because I know that I'm going to get this question, or at least a lot of people are thinking about it, as always has. So before we have the follow-up, there are people out there who are thinking, but traditional lectures can't be bad as I claim, because they all, we faculty learned that way, and look how great we turned out, okay? So my response to that is exactly the same argument that made bloodletting the medical treatment of choice for literally 2,000 years. And the whole point is, to look at this scientifically, you really have to make controlled comparisons. That's what medicine figured out 200 years ago. That's what we're figuring out in education now. And so, for any of you who feel this way, I'll just point out, if you had an identical twin that went through the same way, but was taught in the ways I'm talking about, they'd probably be more successful than you are now. So, okay, thank you.
Well, that was fascinating. I think the first thing is I echo the call for more research into how we teach. My background is as an economist, and I was just thinking, just as we were finishing up there, it was just going through my head. When I started lecturing, no one actually taught me how to teach. It was just assumed, got my education, now I would go and teach. And I'm thinking in economics, there's been lots of discussions recently following, what's perceived to be a crisis in economics, around what we should teach in economics, but very little debate on how we teach it. We have, the development of the new core framework in economics. But again, not much about how we teach it. There is some work, there are some academics out there in economics who teach using experiments and games. But this is very much at the local level, and it's not the norm. I wanted to talk a bit about sort of how we assess universities in the UK. Now, my own experience it has mainly been in the past, as Carl has said, on the assessment of research quality via the Research Excellence Framework. In England now we have the Teaching Excellence and Student Outcome Framework. Now, I know there are some qualms about how we assess universities on that, which is not my point today. But I think it's becoming clear that we do take more seriously the issue of the quality of teaching and student experience in English higher education institutions. And of course, there's an issue with universities being autonomous bodies, and I have to say that I don't have a huge amount of clarity on how science and technology courses are taught in universities, but it is something we need to look at. We do try and link STEM course content. We ask universities to do that through linking to industry with an aim of producing graduates who are skilled and can fill the rapidly changing needs of industry. But again, we don't say much on how they should do that. Now, the Teaching Excellence Framework in of itself is quite broad, and it focuses on an assessment of quality at institution level. And the Secretary of State has recently asked the Office for Students to actually start working on subject-level TEF teaching evaluations. To do this at a subject level will require a framework that relies on a deep understanding of good practice in the teaching of all different subjects. And what we would like to see is how, through assessment of quality of teaching of different subjects, how this will then help students make choices about where to study particular subjects. I'm very interested in Professor Wieman's thoughts on what we, or rather the Office for Students, should be doing in terms of assessing teaching quality at a subject level, and in providing information to students so that they can make informed choices. The other thing I was, I've got a flashing light here. Okay, the other thing I was particularly interested in is something Professor Wieman picked up at the end. We're quite worried so one of our concerns at the DFE is the lack of diversity in STEM subjects, and particularly the lack of women being attracted into STEM subjects. And I'm quite interested again on Professor Wieman's views on actually if we change how we teach, not just STEM subjects, but also economics, where there's a gender problem as well. If we change how we teach, can that increase the diversity of students who come in and take these subjects? I do have one very narrow question. I was really interested in the stuff you talk about short-term learning constraints, and was just thinking, does that then have an implication for how we structure the day at university? Because I was thinking, well, if I go from lecture to lecture, and it's, you've got your 5 to 7 things I can learn short-term, does that have implications for how we structure the university day? Okay, I'll stop there because I'm running out of time, but I could go on forever. Thank you.
Thank you for a fascinating talk. So my background is from the Centre, one of my roles is as co-director of the Centre for Engineering Education, a discipline-based engineering education centre. And so I was very pleased to hear the call for training staff within the disciplines and taking those that have a particular research focus and looking at how we train them. So particularly delighted because just this year we're taking our second cohort into an MSc in Engineering and Education, joint between the Engineering Faculty and the Institute of Education, to try and do just that, which I think really ties into the comment you made at the end of how then we reward the staff that are involved in those sorts of activities and ensure that development of education is as prized alongside research. There are a few things that really struck me about your talk, particularly the idea of engineering and science being applicable across fields just beyond those. I was always struck by a comment, I think, by one of your colleagues, Larry Leifer from Stanford, about engineering being the new liberal arts for the 21st century. Something that these are skills that for the next generation of industry, everyone is going to need scientific and engineering skills, whether it's in big data or AI, that are going to actually permeate across all walks of life in the future. And we need to prepare our students in a very rigorous way to be able to do that. Having led a curriculum reform within UCL, also struck by the scientific approach to evaluation. I think far too often we see great ideas put out there, but with very little evaluation that they be effective, beyond the personal opinion that my students liked it and they seem to get more out of it. So to actually see a talk full of data that really resonates with faculty as to how that will improve the education of their students, I think is very important to convince faculty to invest that time to develop their applications. I think also particularly pertinent is the idea that we see a lot in literature about very novel measures of teaching. I've been involved in problem-based learning, project-based learning, things that really change the classroom setting very fundamentally. So to see options, see techniques that take that classroom setting, can be applied to large classes, and to change the outcome significantly is, I think, something that we need to look across the gamut. I personally am a big fan of problem-based learning and think there's a role for it within many of our curriculum, but actually to see that the classroom setting can be fundamentally changed, can improve student outcomes, I think is something that is a message we should perpetuate across much more of the faculty that we work with. Actually, to your question, when I was a young and naive lecturer, I had the pleasure of spending some time with Professor Lewis Elton, who was part of UCL back then, the physicist, then educationalist. And I asked a similar question about professors, and what, surely it can't be that bad. And he commented to me, but you must remember, normal students don't become academics. And I think that's very important for us to remember, that we have this range of students in front of us. So I guess my final comment is to thank you for a fascinating talk. And I think I should be off to rewrite all my jokes for this year's lectures to make sure they're in line with the curriculum. Thank you very much.
Great. Well, now the floor is open to you and your questions.
Okay, so just some ground rules on the questions. To avoid the slowing down of passing microphones all around. I've said that people will just shout out their questions. I will repeat them so that everybody can hear them. And so if I forget to repeat your question, yell at me. But also, it means that you're going to have to talk loudly just so that I can hear them. Okay? So, yes.
I've often wondered about the ethics of education research. If you know already that there is a better way to do things, and the people who are in your classroom are paying thousands and thousands of pounds or dollars,
Yeah.
is it ethical to give them the old way when you know the new way is better?
No.
And
Yeah. No, I actually spend a lot of time talking with young education researchers about the ethical issues now, and it is quite complicated because on the one hand, sorry, the question was, how ethical, the question about the ethics in research education of doing two treatments when you know one of them is less effective. So, yeah, and so that really has become, in the early days, it was okay because we didn't have so much evidence that the traditional lecture approach was bad. Okay, so it was fine to keep comparing them. Now, clearly, I, as a researcher, cannot set up an experiment where if I have control of how it's taught, where one of them is teaching one way, and then I want to do the comparison. It's awkward, though, because it's kind of like dealing with doctors where where 90% of the doctors are still using bloodletting, and I'd like to show, gee, this is a lot better than what you're doing, but at the same time, I know what they're doing is wrong. The quick answer to that is, yeah, this is a question that researchers do have to pay attention to and are now. And, like in the study that I showed that I had input on of those two lectures, the one lecture versus the other, that was only possible because we had someone who was very sure he was an effective teacher, and he was also pretty darn competitive. And so, he was going to lecture no matter what. We had no control over that, and so we took advantage of that to make that particular comparison. If I have control of it, no, I really can't subject students to something I know is ineffective. And so we have to, what we're then thinking about is, okay, we have one active learning classroom, but we're still figuring out better ways to design and structure problems, and so we can take standard accepted good practice and we then compare it with something else. But if it's not ethical when you're in control of things to have students do something, even though it's, lots of people are doing that or still teaching that way. You can't ethically defend that. Yes?
Throughout your presentation, it almost became evident that you assumed that everybody could actually be an effective teacher if properly trained.
Yeah.
And I was wondering if that's what you implied.
So the question is, he says he's assuming, or felt I was assuming everybody could be an effective teacher if properly trained. And the answer is yes. I mean, at this point, we have well enough defined principles and practices that you follow these things, you'll be an effective teacher. Now, we do know there's variations in how quickly, and that's actually in the big UBC where I got hundreds of comparisons. It's clear that there's a variation in how quickly people, they're become effective and their ultimate level of effectiveness. And that's largely, frankly, that seems to be largely governed by how well or how good a job they can do at understanding student thinking, of sort of, putting themselves in the student's mind. And so some people are not very good at that. And so, maybe they give lousy lectures also. So, they still be much more effective than what they are doing, doing standard lectures, following these practices, even the ones who are least effective. It's just, I'll put it this way. Anybody who's competent enough to get a PhD in STEM can do most of these things moderately effectively.
What have you found is the most challenging in the training, in the retraining on IoT?
So his question is, what have we found is the most challenging in the training of faculty? It's going to seem funny, but it's establishing learning goals for the course. And by that, what we mean is learning goals, or sometimes called objectives, where to really teach these things effectively, you have to, as an instructor, you have to lay out in very operational terms details about what you really want the students to be able to do at the completion of the course. And so, a good set of learning goals, it might have 50 different specific things on it. And what we found is that, and I'm not entirely sure why, I have speculations, but that's just a very difficult thing for most, When I went into this change, and it was okay, the first thing you want faculty to do is sit down and make a clear list of learning goals, and then those will guide the instruction, the design of, the activities, the assessment, and so on. And faculty just had a terrible time doing that, it was just very difficult. And in fact, what we found is most of the time, they'd sort of have some tentative, difficult thing. They'd introduce these active learning practices where then they would be connecting up with students much better, and they'd have a much better idea of what students were thinking and struggling with. Then they could iterate better in terms of establishing those goals. Then they could make everything work better. But it's not at all what I would have expected would have been the most difficult, but that's what it was. Yes.
I would be very grateful to hear your thoughts on the gender issue that was raised before. But also, what about variation in prior attainment and subsequent attainment? Did those who came in with lower prior attainment catch up, or was there still the same variation at the end?
So these are two areas of current research by a number of people, but in particular, my own research group. And so in terms of the gender issue, we and others are looking at this more broadly. I showed how we moved the distribution up. Now the question is, how do you pile it all up at the end, right? And so there's some indications that not just gender, but other students and other groups who are traditionally performing worse, that these methods help them improve. It's a mixed, I won't say we have great understanding of it and we can give you things that are going to make a big difference yet. We see some indications. It's closely related to the second one, though, which is the preparation issue. And I'll refer you to a paper which is just been published like 3 weeks ago in Physical Review, Physics Education Research. And what we did was we looked at, and we did this, ended up looking at 3 rather different institutions and saw the same thing, which was really dramatic, which was really surprising. We looked at performance in Physics 1, basically, which is kind of standard every place. And we tried to find out what was a predictor of final exam performance. And we started out with the same thing that a lot, basically, every institution I know that's looked at it sees that in that class, women, underrepresented minorities, and first-generation college students perform typically at the level of a quarter to a half a standard deviation lower than the average, okay? And so we set out to find out, okay, what are all the factors that go into this? What the quick answer was, when we did a bunch of statistical modeling, prior preparation was everything, okay? And with two rather crude measures of prior preparation, which was the SAT math score, which is in the US a national kind of math test, the SAT math score and a simple, crude pre-test of physics background knowledge that we gave the students the first day, those basically accounted for about 30 to 35% of the variation in final performance in the class, okay? And once you included those, there weren't any other variables that had predictive value. So women, it didn't matter. Underrepresented minorities, didn't matter. First generation college students, those were simply secondary indications of who was less prepared in physics, from secondary school. And so we saw it in Stanford. We saw in Colorado, which is at University of Colorado, which, Stanford admits 0.1% or something of applicants, and you have to be in the top 1% of tests, or 1/10 of a percent in test scores. Colorado admits 2/3 of all its applicants, totally different population, and yet the exact same model was true, 34% of the variance. And so what we've concluded from that is that and Cornell was also, we got data in there. What we concluded is that there must be something fundamental in the way instructors are teaching, which has them biased to essentially teaching to the top third of the incoming preparation, and therefore really stacking the deck against these ones who come in underprepared. And in the US, we can trace these under-preparation really is almost entirely economic. I mean, you come from the poor, correlates very strongly with coming from the poor poor in the sense of economically poor school districts. So we think it's all about preparation, and some indication the teaching methods help some, but not as much as we'd like, and that's really an ongoing research project right now, is to figure out how much is possible to change and how much it depends on teaching methods. Yes?
Just a comment. When I'm a mechanical engineer in my first degree,
Yeah.
and I could say, you're talking about two different ways of teaching, about memorizing or about thinking, but I was thinking two different ways. I was taught about the past, but not about the future. So we are teaching about what we have now. Of course, the world is changing very fast, but these kids in the classroom, they are going to live in the future. They are going to create the future.
Yeah.
So how do we manage to do that? Also, they will be more than scientists. They will
Okay.
be more than engineers. They will be human beings.
Right.
Okay. How do
Okay.
we,
Yeah. So my point is, what?
The question?
Oh, well, there wasn't really a question. His comment is on. You want to repeat it?
It's basically teaching for the future.
Yeah, teaching to the future. How does this relate to that? So what I would argue is that any particular subject material, especially in engineering content, it's going to be obsolete very soon. So what can we pass on to these students that's going to be of value? And I would argue it's the same thing whether they're going to be an engineer or they're just going to be a good citizen. And that's not the topic so much as the reasoning processes, and I put it in very specific terms, the decision-making processes used by experts in that subject. And that those are that's the core of our human knowledge, and that goes well beyond any particular content. And so it's applicable in terms of being good citizens when you have to make decisions about, what society should do in terms of energy choices or, genetically modified foods. It's those kind of ways of thinking will guide you there. Also, in the same way, being an engineer I'm going to be I'll be more than surprised. I'm pretty certain that, in 50 years, engineers will be doing completely different kinds of things, but they'll be using very much the same decision processes that they are now that, made engineering what it is to do that. So I think that the things I'm talking about here really is teaching the students for the future. Let's see. Yes.
Earlier on in the talk that we heard, there's a teaching excellence framework is going on in the UK, which is measuring quality of education. Do you have any insights on how to measure that so that students can choose a degree course on the basis of that quality?
Yeah, so what I suspect my approach is quite different from what they're using here. But what I argue is the way to measure quality is to completely characterize all the teaching practices used in a course. So that involves not just what happens in the course, but what kind of exams and what kind of supporting material, et cetera, and look at then. And so we developed an instrument to do that in a rapid, efficient way called the Teaching Practices Inventory. And it's got 62 items, but believe it or not, people can fill it out in 5 to 10 minutes. A lot of work went into that. At the end of that, you have a very thorough, well-informed, characterization of the practices used that instructor used in teaching that course. And we then can have a rubric, a scoring rubric that goes through it and says, okay, of these, you now know all the things they did. Which of these is there research showing leads to better learning, okay? And so, then you have an effective teaching practices score. And, hopefully soon universities will start recognizing teaching practices really do matter. They'll have that data available, and then students will be able to look and see, gee, University College London, they're using these methods at this level of frequency, whereas Imperial, they're, somewhere else. So I'm going to, so that's what I would argue. So we have the methods for doing that existing, and people in the U.S., I've been talking about this, but that's a very slow process to get that kind of change adopted. Yes.
We learned a lot about learning today, but I think assessment and marking is very important for us here at the university, right? So today it seemed as if you were evaluating your methods towards the same type of exams, but do you think that we have to change the way we are assessing the decision making, or should that go, is that interfering with the learning process? Should that be at the end, or what's your...
Yeah. So his question is a very good one, which is, do we need to change the assessments and the exams that we use? And I would say that depends on the what is happening in those assessments and exams. If you're assessing learning by I wouldn't want to point to any fingers here. I'll just say, broadly speaking, in the U.S., the students are locked in a room, given access to no other resources, and told to solve a bunch of stuff which involves memorizing a whole bunch of things which any reasonable functioning scientist or engineer would quickly just look up. Okay, that's a totally that assessment is completely inauthentic. It has no connection with actual real performance of their, of the job, and so it's really meaningless. And so if you want students to learn to really think like experts, you should assess them by giving them tasks that have them think like experts, giving them, the same kind of opportunities. I'm willing to say, no, you can't run and ask somebody else, which is what any, real experts do most of the time. but they should, access the same kind of information, have very much the authentic tasks which involve having to make those same kind of decisions that we listed there. That'll be a much better, much more meaningful assessment. Now, having said that, if you go and look, at all these interventions and what they do, how much difference they make on the standard assessments, the more the assessments are kind of about memorized information and procedures, which is the vast majority, frankly, they don't show any difference, and you wouldn't expect that, because that's not what you're teaching. To the extent they do involve actually more reasoning and thinking, then you see bigger and bigger differences in the kind of assessments my group is now working on, where it's really based very much on very explicit decisions and putting realistic scenarios. There we see giant differences. We see these Stanford medical students who are, passed millions of exams with spectacular scores that are basically memorization, and they don't know how to diagnose a patient at all. They have all this knowledge, and they simply don't know how to organize and make decisions with it, and that's really easy to assess. You just ask them to do it and why, and it shows up. But the bottom line to your point is, we need assessments which are really, in some sense, more valid measures of the real learning we care about ultimately. We found in working with faculty to change their teaching, that happened very quickly and immediately. As soon as they really started thinking about what they wanted to learn, they would change their exams pretty dramatically, actually, to capture that better. Way in back. But you have to talk really loud.
You framed learning around the transformation of human brains. And I would like to ask your perspectives on the role of other parts of our human beings, our physical bodies, our emotions, on the process of learning, and specifically on the relationship between cognitive learning and emotional or affective learning.
So the question is, what are other parts of the body, but also other parts, affective and emotion, that's still other aspects of the brain. So other aspects beyond cognitive and other parts of the body. So first, I'll say with respect to other parts of the body, I don't know of any. Everything we look at happens in the brain. And I'll just, I'll leave it at that. In terms of these other aspects of the kind of emotional or affective, those come in a very important way, mostly through the motivational aspects that, and therefore it's absolutely critical they be addressed, and they're part of what you have to think about in the teaching. But so they are things that matter just because in a large sense they govern how people do other things. Okay.
Oh, I just think one more question and then we're up for time.
Okay. How about we take two? Those two were both very eager. Yes.
Can you comment on the relatively recent data set coming out of the US Military Academy on the flipped learning in maths that seems to contradict the rest of the literature? Is it a question that the field needs to get much better at describing methods and also measuring what are we really measuring in these experiments?
So his question is, he's referring to a study coming out of the Military Academy, US, sort of giving different results. I'm not sure exactly which study you're talking about. I will say I've looked at a number of military academy studies, and they give, and sometimes they agree with this stuff. Sometimes they give quite conflicting results. And but having looked at this stuff in detail, the life of a military cadet is profoundly different from a university student. And so they have a bunch of factors that come in that are really different. And so I've learned to be very tentative about interpreting and taking a broader view of any of the things that come out of those situations, just because there's a whole lot of other factors going on in their life that are quite different from normal students. Okay, last question.
Yeah, so one barrier to learning is that students sometimes do not prepare or do not attend the sessions. So I was wondering whether you found some correlations between attendance and research-based learning, or whether you have some recommendations on how to increase attendance and increase preparation.
So his question is worrying about attendance and how that's related to this. So the first thing is this research dramatically increases attendance, okay? And that's universal. And I mean, in fact, that was the first thing that the Stanford faculty were so struck by is, gee, you know, attendance was 50 to 60%. Now, all the students are all coming to class all the time, okay? And so, I mean, and I think that's partly they're supposed to be producing something, they get marked on it, but the main thing you hear is that's just a much more effective use of their time. They're actually learning something, and so it's worth investing that time. You mentioned also about the preparation, having them prepare for class. That's something we studied at UBC, and you know, if you go look at the references there, how to get students to prepare ahead of time, and basically we have a set of things that say, you do this, and they'll prepare ahead of time, okay? And you know, it's now been tested and repeated over and over again. It's just, and it's, you know, this will give me an excuse to make a final comment here, is that all of our work says students are actually incredibly rational. And so if they're not doing what you want, it's because you don't understand why they're making the decisions they are. And so things like preparing ahead of time, we just study them and we do detailed interviews with them and we find, oh, okay, so we need to do this, and then that convinces them. And that's worked over and over again. So on that, you know, on that note, I'll say, you know, you have to just think of your students not how to get more effective learning, but also in terms of if they're not doing what you want, you need to understand their motivation, decisions better, because you may not agree with it, but it's almost always a sensible, rational decision based on the environment they're in, and if you adjust that environment properly, they'll end up doing really exactly what you think is best for them. Okay? Thank you.
Well, I just wanted to thank you, Carl, for a really incredibly thought-provoking and stimulating talk. It really was incredibly interesting, and focusing on the transformational nature of education, for me, is what it's all about. Thank you very much indeed. And can I thank the two other speakers, Mr. Rahman and Professor Mitchell. I'm happy to say there's drinks outside, so enjoy a glass of wine. And thank you, all of you, three of you, thank you.